You are correct, Janabelle. I have not been recording. So anyone tuning in has just missed the first three problems, 45, 47, and 56. Luckily, I did record it in Summer 1. Those students will have to get the link from me for Summer 1 to get those three problems. Shoot. I can't believe I forgot to do that. Thank you, Janabelle. I'm getting more senile as this summer goes on. Okay. We are going to continue to use that formula for number 57. Olivia, will you read us number 57? We're doing homework number 4. We're doing chapter 4, number 57.
Okay, 57. Using Newton's version of Kepler's third law. A, calculate Earth's approximate mass from the fact that the moon orbits Earth every 27.3 days at an average distance of 384,000 kilometers.
Okay. Students, you'll notice that I write down the givens whenever I have to solve a tricky problem. Extracting the givens with their units is a classic way to begin problem solving. Now, in this version of the formula, we're going to use NK3, and we're going to use it solved for mass. Normally, I show you the algebra. Maybe I'll do that during today's class. But the formula ends up coming out like this. The total mass, which is M1 plus M2, is 4 times pi squared times a cubed divided by g times p squared. In this case, the total mass is the mass of the Earth plus the mass of the moon. And I believe they give us a hint at the bottom of the problem, Olivia. They let us know that the mass of the moon is roughly 1/80th of the mass of the Earth, right? At least the old version of the text used to do that. $1 out of $80 is not a lot of dollars, so we can neglect the mass of the moon. The issue that we have here, and I need to go kind of quickly here because we took a long time on that previous problem, is we need to convert 27.3 days to seconds. We need to convert 384,000 kilometers to meters. I'm tempted to do that for you, but I really think it's a better idea for you guys to practice your conversions. So Olivia, why don't you start us off? Can you do 27.3 days? And can you help us convert that to seconds using dimensional analysis?
Yes, okay. So you would write 27.3 times the
you meant
days.
You would write 27.3 days. Isn't that what you meant to say? Okay.
Yeah, I saw you writing it and then my mind just skipped over it. But days.
Right, but guess what? I'm not going to be saying it during the test.
Yeah.
So if you try to write that and do dimensional analysis, you host, okay? You're totally host without the units. All right.
So be 27.3 days times the division bar.
Yep.
And you said from days to seconds, right?
Sure.
Okay. And in the numerator, you'd write hours.
Yep.
As the and then in the denominator, you would write days.
Good. I'm going to give you a tip here. We're going to try this a different way this time, Olivia. Let's get all of our units in place first, and we'll put the conversions in at the end. We'll do step 3 a bunch of times, and then we'll do step 4 a bunch of times.
Okay.
So what's going to be the next set of units?
Then it would be
your days cancel now.
Yep. So that would be minutes in the numerator.
Yep.
And hours in the denominator.
Okay. What comes next?
And then it would be seconds in the numerator, and then minutes in the denominator.
Okay. We can say top and bottom if that's easy. Okay, now
Yeah.
give me the conversion factors.
Okay. So for hours, it would be 24.
Where do I write
And
that?
oh, I'm sorry. And then the top. 24 hours. Yep. And then it would be 1 day.
Fine.
And then you would write, how many? 60 minutes on the top, and then 1 hour at the bottom, and 60 seconds in a minute.
Nicely done. Okay, punch them up for me.
So for in the calculator, you would just do, it would be 27. You would start with 27.3
Times 24 times 60 times 60.
Okay.
You don't need to divide by 1 because that's not going to change it.
That's pointless. Okay.
I mean, you can if it makes you feel good, but
Yeah. Okay, so I did do it right the first time. So it was, well, that's, so I have to write it in,
what do you got?
well, I got 2,358,720.
Give it to me in scientific notation with 2 sig figs.
2 sig figs? Okay. It would be 2 point, no, yeah.
2.4 to the 6th power?
Thank you. 2.4 times 10 to the 6 seconds.
Yes.
Right?
Yeah.
All right, fine. Okay, now we got to do 384,000 kilometers. We got to convert that to meters. How many meters are in a kilometer?
Would it be 1,000?
Right. Okay, can you do this in your head? What should I end up with there?
Uh, 384 times 10 to the 6th power.
Good. That's how we play ball. Okay, now we're ready to plug those 2 numbers in. The mass of Earth will be 4 times pi squared times open parentheses 384 million meters cubed over big G, 7 times 10 to the minus 11 meters cubed per kilogram per second squared, times the period, which was 2.4 million seconds. Squared. Punch them and crunch them. Can you hold that up a little closer, Megan? It don't look good. You did something weird, Megan. Hold up what you get to the window so I can give you a thumbs up or a thumbs down here. I'm gonna need a little tea break. We're probably gonna save the last problem for during the lecture. Okay, Olivia, what do you got? Show me. Nice and close. No. No.
I think I messed up on the bottom part again with the. So for the bottom part.
Adrian, you got it. Wait, Megan, show me yours again. Adrian, you're good. Hey, Megan, you're good too. So tell me how you messed up on the bottom.
I think the parentheses keep throwing me off for some reason. So for the bottom part, would I put the parentheses?
No,
wouldn't.
same
Okay.
same issue as before. Those parentheses aren't there for your calculator. They're there for the units.
Okay, I'll
So
try.
Olivia, you would do 7 exp negative 11 divided by 2.4 exp6 square key equals.
Okay, all right.
Janabelle, don't look right. Let me, no. Did you forget to cube your A? You're off by many powers. Did you forget to square your period?
Let me try. I'm gonna say it out loud now. I'm gonna do 4 times pi
Squared.
times 384 exp
Uh-huh.
6
Uh-huh.
squared
Cubed.
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 4 pi squared.
No, 4 times pi squared. Not 4 pi squared, 4 times pi squared. Andrew, what are you getting?
I don't think I'm getting it right.
Well, can you show me what you're getting?
I've had like 3 different answers every time I've tried.
Well, what's your latest one? Maybe your latest one is good. No. Olivia, you got it. Yimmersey, you're just a shadow to me. I can't see you're backlit, so I don't know if you want to show me yours too. You know what the faster way to do things? Nick, not quite. All right. Many of you are getting it wrong, so you're going to have to just watch me. Clear it out. Try to keep up with me, okay? Clear it out. Good. Watch my moves. 4 times pi squared times 384 exp6 shift cube divide by 7 exp negative 11 divide by 2.4 exp6 square equals. Oh, some of you are forgetting to hit equals. I can see that now. Show me the right answer. Everyone hold it up. Wait, wait, wait. Let me go to gallery view. Keep it there, keep it there, keep it there. Yes, 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 yes. And Megan, you got it, right? Okay. All right. Guys, Yimmersey, did you get it? Oh, yeah, that's good, Yimmersey. You got it. Awesome. This will get better, okay? This homework represents a significant step up in the work that we've done so far. So this is always a growing pain for every class, okay? This homework always sucks. In fact, today I was rubbing my temples thinking, oh, God, okay? So it will get better. Trust me. Okay, so what's our final answer then? 2 sig figs with units.
5.5 times 10 to the 24th kilograms.
Good. You know what's kilograms because it's a mass. Put a box around it because that's a classy move. Okay, let's do part B now. Olivia, I believe you were our reader.
Yes. Okay. So part B. This is 57. Yep. Okay. Calculate Jupiter's approximate mass from the fact that its moon Io
Yep.
orbits every 42.5 hours at an average distance of 422,000 kilometers.
Okay, I'm gonna speed things up here because you guys are a little pokey. I'm gonna convert 422,000 kilometers to meters. Kilometers to meters is 1,000 to 1. That gives us 422 million meters. We're now gonna convert hours to seconds. 42.5 hours. If I go hours to minutes and minutes to seconds, 60 to 1, 60 to 1. Actually, I'm going to cheat and I'm going to do 42.5 times 3,600 because I'm crazy like that. 42.5 times 3,600. And that gives me 153,000 seconds. I'm now ready to plug it into the equation. Ignoring the mass of Io, which is a pretty safe assumption, the mass of Jupiter is then 4 times pi squared times 422 million meters cubed divided by big G, 7 times 10 to the minus 11 meters cubed per kilogram per second squared times 153,000 seconds squared. Why don't you guys just focus on trying to punch that up correctly? Sorry, my handwriting was a wee bit sloppy there. I just needed us to kind of push forward a little quicker here. I'll look forward to getting your answers. What do you got, Olivia? Good, that's correct. Yimmersy, you got to get a little closer. Yimmersy, you have it correct. Megan, you have it correct. Something's not right, Janabelle. You're too big. You might have forgotten to square your period. Nick, you're too small. You might have forgotten to cube your A. Adrian, what are you getting?
An error message.
All right, so show me your punch. Show me your clean punch. Just hold it up to me. Hold on, I gotta full screen you. Keep it right there. Okay, so you're still doing it piecemeal. Remember in Return of the Jedi when Yoda, I'm sorry, in Empire Strikes Back, when Yoda says to Luke Skywalker, "Hear you nothing that I say."
I put the parentheses because it was in the equation and I forgot it was for the reasons of units. So
But
I
also, Adrian, one clean punch, not your piecemeal punching. Do you understand what I'm saying?
put it all in one.
Can you show me again?
You can see where I tried it and it gave me an error twice.
Oh, is there more to the, oh yeah, I see it hasn't scrolled.
Yeah.
Look, you have to the power of 77. It's power of 11, right? correct?
Did I just press the 7 key a bunch of times? Oh,
I think
no.
it's, I could see right there, it's power of -11. It looks like you had 77. Maybe that's what's, no, but that's not going to give you the error message. Also, can you show it to me one more time?
It gave me an overflow message, and you're right. I accidentally put -77 instead of 11, and I
Can you
don't
hold
know.
it up? Can you hold it up again? I want to look at your moves. Hold it up.
Like I said, I accidentally put it to -77, and
So what you're going to do is you're going to delete those parentheses first. We have to cut down on the number of characters so I can see what's going wrong. And then I need you to scroll back so I can see what the rest of your line is. Janabel, hold that up there. One sec. No, you're too high. You're getting this. What are you doing? How did you get that? Yeah. Janabel, you forgot to square your period. That's what's going on. Janabel, hold on, Nick, let me see yours. Nick, bring it back a little bit, so focus it. That looks good, Nick. I think you got it. Janabel, you're forgetting to square your period. I just tried it on my calculator. You got to do it again, hitting p squared. Anyone else? Adrian, I want to see your calc so I can see what's going on. Where are you?
I'm still punching it in because I accidentally hit clear instead of.
Let me tell you how to do that in the future. Instead of punching it in, you hit second function entry, and it'll bring up the last thing that you punched in, even if you hit clear. Do you understand what I'm talking about? Probably not. Here, I want you to try something. Delete everything on your screen, okay? And now on your calculator, I want you to hit second, and then go to your enter key and hit enter. What do you see happen? The whole thing shows back up again, right? That's how you use that calculator. Okay, scroll around and clean it up and show me what you got. I need you to get rid of the parentheses around the 422 for starters. Get rid of those. And then show it to me again. Just scroll over and delete them. Yeah, now you got it.
Like I said, it was an overflow error from putting -77.
Okay, well, don't do that no more. Janabel, did you clean it up? Oh, I can't hear you because you're muted, buddy.
Sorry, I'm frazzled because I don't know if I keep putting times EXP to the 6 or if I'm just pressing EXP. You know what I mean? I get confused sometimes, but I don't know how to press time.
You don't need to hit times, just EXP. Janabel, why don't you everyone who isn't getting it can follow along with me one last time. So Janabel, I move kind of quick, so
Yes.
let me find your face here. Okay. 4 times pi squared times 422 exp6 shift cube divide by 7 exp -11 divide by 153,000 squared equals. Hold that up to me. Yeah, now we're talking.
I did get that once and I psyched myself out.
Oh, I see. Okay, that happens. Well, these are some growing pains that we have to go through. Let's round it to 2 times 10 to the 27 kilograms. Okay, listen. We need to get on to our daily lecture today. So here's what's going to happen. By fiat, we are canceling part C, and we are going to cancel part C, and 58A will be an in-class exercise using escape velocity. Everyone follow me? You'll still be responsible for turning in 58A, but that's going to be an in-class exercise. Capiche? All right. That was a lot of struggle. I know. I knew it was going to be like that. You guys want to take a little pause before we start our lecture? That's good for us, right? All right. It's currently 12:15 almost, which is terrible. We will start at 12. We'll give ourselves 10 minutes. 12:25, okay? 10-minute break. I'll see you guys on the other end. Okay, everyone, I'm back. I'd like to remind the class that there is an exam on Monday. That's important. Because we're getting a late start today, and because the lab is going to be a little messed up, I'm probably going to use the lab time to finish what I'm talking about and to like go over the format of the test and talk about those issues. So you won't have a lab today, and I will try to get you out earlier than normal, but we might have to go to like 3:30 or something, okay? I think it'll all balance out in the wash. We'll take our normal tea break at 1:30. Okay. In your last class, you learned about Newton's version of Kepler's laws.
You actually asked us to remind you to go over something.
I think I asked you to remind me about the second law. But first, I want to talk about the third law for a second. I can't remember if I got into this on Monday, but for NK3, as you know, is a very important formula in this class. And what I would like to do is I would like to put the key variables in blue. The key variables are the period, the distance, and the total mass of the system. This version of the formula actually works for any two orbiting masses. Kepler's version only works for planets that orbit the sun. Now, you may not remember the small details, but if I were to share my slideshow with you guys, and let's quickly call up our couple of our lectures here. We're going to need the history of astronomy. We're going to need celestial mechanics. We're going to need light and telescopes. So what I'd like to do is I'd like to call up the history lecture. What am I doing wrong here? Okay. I wanted to remind you guys that if you look at the time periods of Johannes Kepler, when he was modeling the orbits of planets as an ellipses, it was somewhere around the year 1600. And Johannes Kepler was actually a contemporary of Galileo. In fact, I think Galileo was born 10 years earlier and died 10 years later than Kepler, if I have that right. Yeah. So basically, Kepler and Galileo were right around the same time period and close to the same age. And they were both famous scientists of their day. Galileo was working in Italy, whereas Kepler was in Germany. But because these were famous men of the day, they knew of each other and they occasionally wrote each other letters. When Galileo first observed the moons of Jupiter revolving around the planet, he kept careful notes of the dates and times at which he saw the planets oscillating back and forth. And he wrote to Kepler about this and said, hey, dude, I don't know if you know this, but I built a telescope and I looked at Jupiter and I could see all these little moons going around it night after night. And Kepler wrote back and said, wow, that's really interesting. Do you know about my law P squared equals A cubed? It's supposed to work for planets going around the sun, but why don't you give it a shot? Why don't you take my P squared equals A cubed and see if it works for the moons going around Jupiter? That would be kind of interesting. So Galileo dutifully went out and he observed the moons. He waited till they went back and forth in front of the planet. He even observed their distances from Jupiter, their angular distances anyways, and he cubed them and squared them, and guess what he discovered? It didn't work. P squared equals A cubed didn't work. And after it didn't work, Galileo actually lost respect for Kepler and thought he was a crappy scientist because his famous equation wasn't really working for the moons of Jupiter. Of course, what none of them could have realized is that the reason that it wasn't working is because they hadn't accounted for the effects of gravity. Of course, Isaac Newton could see what was going on. He knew that if you were going to have, where are we here? If you're going to have two objects orbiting each other, Jupiter and a moon, you'd need to include big G in the sum of the masses to fix P squared equals A cubed. So we introduced NK3 to you in this format because this is how it was historically developed. But in reality, no one actually uses this version of the formula because it's not useful. Of the three quantities in blue here, which do you suppose would be the easiest to measure if you were Galileo looking through your telescope? Would it be easiest to measure the period, the distance, or the mass of those objects?
Distance?
The period?
The period is the correct answer. Was that you, Megan, that said period? Who said period? Sorry. I can only see a few of your faces at a time.
I did. I'm just eating lunch, so I stopped my video.
That's okay, Adrian. No problem. So Adrian says period. Why would you say period, Adrian? In the shadows.
Because it is extremely difficult for someone back then to figure out the distance, and because it's not like it's a thing that they can hold and measure easily, but they can watch it go through the sky.
Yeah, so in other words, I agree with you, Adrian, with one exception. The period is the easiest to measure, the distance is the second easiest, and this is the hardest. But to Adrian's point, her idea is that if you see the moon here, all you have to do to measure the period is to wait for it to go behind Jupiter and then in front of Jupiter and back, and then you just measure the time. That's true. For this reason, P is known in science or astronomy as the observable. This is some adult language that I'm using with you here. P is the observable because that's the thing that you actually measure. Adrian, the distance is not as hard as you might think. The way you would get the distance is you would use the small angle formula. You would measure the angular separation between the moon and the planet you would know the distance to Jupiter by doing p squared equals a cubed. And then you could use the small angle formula to get S, the separation between the moon and the planet. Remember the small angle formula? You know Jupiter is 5 AU away because you plug in its period to get its distance. You use p squared equals a cubed, the Kepler version. And then you plug that in there, you measure the angular displacement in your telescope, and that's how you get the distance between them. Pretty clever, right? Maybe I'll make you do that on the test on Monday. Wink, 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 wink. Okay. That's something that you should be able to handle. So A is not as easy as the period, but it's also an observable. M, the mass, this is hard. I mean, to your point, Adrian, it's not like you can step out to Jupiter and give it a dunk on your Stop and Shop scale. That's why the real version of NK3 is to rearrange it and do NK3 solved for mass. And you guys just saw that in your homeworks. But I wanted to remind you of what's going on. You have that the total mass of the system, M1 plus M2, is 4 times pi squared times a cubed over gp squared. This is such an important formula in astronomy that you need to learn it to understand why astronomers do the things they do. It's sometimes referred to as the cosmic balance beam. Obviously, you're going to be using it several times on your test because you used it several times in your homework. And I'm one of those teachers who has test questions similar to what you do in your homework.
Is that, I know you said you're still writing down the test questions, but I did look them up on Blackboard, or I don't know if those are the ones from last semester, or those are the same ones you're adding on to.
Oh, I have to add on to them. Actually, you're not supposed to be able to look at that yet, so I'm surprised that it let you look at that. I should have not done that, but they're going to be tricky, you know. Either way, the test is going to be open book, so I guess it's not a big deal. What was your impression of it?
Oh, I just wanted to ask if it was that exactly, because I was able to pull it up, and I just wanted to know that.
Yeah, I mean, I think the idea is going to be I have to add more to it. I see what's going on here. Did you see it as a multiple choice test or as a Microsoft Word document?
I see it as, let me see if I still have it. I see it as a Microsoft Word.
Yeah, no, it's probably going to be a little different than that. So just ignore that one.
Okay.
Actually, there'll probably be some questions that are the same.
Okay.
I meant for that to be hidden. But in any case, if you saw it, it's not that big of a deal. You're going to have to do those questions. It's such a long test that if you had already done all the questions, you'd almost deserve to have cheated. If that, you know what I mean? It's not like you can cheat just because it's such a grueling, long, difficult experience that you're only going to have the strength to do it once. Does that make any sense?
Yes, yes. Mm-hmm.
Okay. Unless you're crazy. If you're crazy enough to do the test twice, well then you'll probably actually learn quite a bit from it. So I'm okay with that. In any case, that's not going to be the way I present it to you, Janabelle. See, that's the Microsoft Word version. I'm hoping that it'll show up to you guys as like a multiple choice where you click through the buttons and I'll be able to do the statistics. I haven't finished with it yet, which is another reason why I should try to end class early today. We'll get around to that, okay? All right, let's talk about Newton's version of Kepler's second law for a moment. Did I answer all your questions? I didn't know if you were just kind of wondering about the format and stuff. I'm going to go over the format at the end, Janabelle, at the end of our lecture today.
Okay, sounds good.
Sorry to interrupt, but can you put the small angle formula back up? I didn't get to get that down.
Sure, that's fine.
Thank you.
you should have it in your notes from before, but the small angle formula, S equals theta times D times 2 pi over 360 degrees. That was in our first lecture. But in that case, we were trying to calculate the diameter of the moon. In this case, it's a little bit different. In this case, S represents the separation between the moon and the planet. Theta represents the angular separation between the moon and the planet, and D is the distance. So you're observing from over here. So that's your setup. Adrian, drawing the picture is just as important as writing the formula down, as you may know. Adrian, I'll probably walk you through a sample problem on that, the office hours, the day of the test, okay?
Thank you.
By the way, did you guys know that there's a comet that's made an appearance in our local skies? I think Tim might have been talking about that. The comet's name is Neowise, and here's a picture of it. I've since been checking out its trajectory, and if the skies are clear, if you have an unobstructed view of your northwestern horizon, in the next week, you should be able to see it getting a little higher in the sky below the Big Dipper. Unfortunately, most people have a lot of buildings and trees that block the lowest portion of their horizon. So if you have a bunch of trees and buildings and hills nearby, it might block the comet. But if you have a clear view of the northwestern horizon, I'm going to try to view it from the rooftop of the Peerless building tonight. I'm downtown, and that means I've got a lot of light pollution. But I'm hoping if I go up to the top of the Peerless skyscraper, which I have access to, I'll be able to look northwest and see it tonight. It was too cloudy last night, but I'm hoping to go up tonight and see if I can see this bugger. Supposedly it's very beautiful, and people have been taking photographs of it, and it's a classic two-tail structure to the comet. There's a bunch of photographs of it. It should look something like that in your local sky. Not every day do you get to see a comet, so that's pretty cool. Nick, did you have a question about that?
If I get my camera back in time because my camera broke, I'm going to try and get a picture of it. But
No
I
way.
don't know if I'm going to be able to get it back in time.
Yeah, do you have a tripod, or are you going to try to just hold it and point and shoot?
I'm going to try and hold it. Actually, I should be able to see it right from my window, so I should be able to keep it steady enough.
And if you have an unobstructed view of the horizon, some tips there, Nick. You know, astrophotography is something that I'm into too, and I'm going to try to get a picture of it. Yeah, if you have a small telescope that you can attach your camera to, that will obviously help. But you don't need too much magnification. Do you have like a DSLR with a telephoto lens?
Yeah.
Yeah. That telephoto lens is like a telescope, so you might actually get something with that. I'd recommend a tripod to keep vibrations down, and you're probably going to want to try to do a long exposure photograph. Another technique is to take multiple short exposures, a few seconds each, and then stack them in Photoshop. Because what happens is, you're getting background noise from the sky. It's different than shooting a wedding because photons are at a premium. You're getting a weak trickle of light. So what you want to do is you want to take many, many images and then stack them to build up your signal to noise. So I'd recommend if you can take like 21-second exposures, which might sound like a long time to you, but for a faint comet might be decent. 21-second exposures, 31-second exposures, and stack them. You may have to go into Photoshop and change their registration because the sky will be rotating as you're snapping the photos. There's a little bit to it. If you want to learn about astrophotography, there's a pretty cool website by Starizona. Astrophotography is its own crazy thing, Nick, and it's something that I'm obviously into.
Yeah, I just into it.
Huh?
I just started getting into it. I bought a camera a few weeks ago, but for whatever reason, none of the settings would change properly, so I had to return it and exchange it.
Okay, well, if you are into it, Nick, there's a lot to learn about it. Guide to CD imaging. This guy has a wealth of resources, but if you want to just start learning about CCD imaging, he'll start telling you all the craziness, and it'll just give you a sense of where you can go from there. So I'm plopping that into your chat room for anyone who's interested, but especially for Nick, because you know, I get excited when I hear that someone's going to try to take a photo of a comet. That makes me happy. So if it comes out looking good, Nick, you be sure to share that with me, and I'll dump it in the slideshow, okay? All right. By the way, I have some cool photos that I've taken with students in the past. If we weren't in the middle of the COVID thing, Nick, I've got a little group of folders of astro photos that I've done with students in the past. I think one of the best that we did, this one was quite a bit of work, but we took this picture of the Orion Nebula, which is pretty dope. You can see some gas clouds. We were only using a 1 megapixel camera, and there's reasons for that. But I've got a bunch of cool photos. One of my former students took this picture of Jupiter, which I may have showed you last time. He did that with a DSLR camera. There's Jupiter and the Galilean moons, kind of cool. We got a whole damn setup there.
Yeah, I have a really old, really powerful telescope that I got from my grandfather, so I'm gonna try and figure out how to set that up as well.
Yeah, what you need is you need a T adapter or a T ring. So if you have like a telescope, you have to know what type of telescope it is, but an SCT T ring for a Canon. I know I'm kind of yapping away, guys, but this is something that's related to the class, and if people are interested, come on, you dork. This kind of thing here, they call it sometimes a T adapter. It depends on which type of camera you have. They have different ones for different cameras. But just so you know what you're looking for, this ring is all you need, and you can basically turn your telescope into the telephoto lens. Do you see this thing? It's a little ring that this side clips into your camera, and this side can thread onto the telescope. So I'll put that in the chat log too, so you can learn a little bit more. If you have one of these, unfortunately, there's a million different types of T-ring. It'll be different depending on the telescope and on the camera. So you may have to do some playing around, but the T-ring only costs 20 bucks. And then you're going to be off to the races, and you're going to enter a whole new world of cool, okay? Okay, back to the show. So let's talk about some other things that Newton did that we would like to discuss. One of them, and I'm going to skip the pretty pictures here, is Newton derived a formula for something called the escape velocity. And we're going to call the escape velocity V subscript ESC. I think the idea was, because Newton, all right, I told you I was going to not do the pictures, but I can't really help myself. I have no control over this. Let me show you an appropriate slide and get you to think about what's going on here. I believe the way that Newton might have imagined this is he imagined that if Earth did not have an atmosphere and it did not have any air friction, if you fire a cannonball, the cannonball's path is a parabola because it's kind of like trying to orbit the center of Earth on an ellipse, but then it falls down and it hits the ground. So when you throw a ball through the air, its trajectory is always a parabola, which can be thought of as a piece of an ellipse. He realized that if you could fire the ball fast enough, the parabola would go past the curvature of Earth, and it would actually go into an elliptical orbit. And that sort of gave him the tip-off that there would be one speed called the escape velocity, which if you could travel at this speed, you would be able to leave the gravity of your planet. So let me define the escape velocity in this way. The escape velocity is that unique speed that any object needs to leave a planet of mass capital M and radius capital R. And the cartoon picture should be of a planet the planet has radius R and mass M, and you have something like a rocket ship which is trying to blast off with some escape velocity. Those are the parameters involved. The formula goes like this. The escape velocity is the square root of 2gm divided by R. Now, students, this brings us around to question 58A. In question 58A, they asked us to calculate the escape velocity of Mars. But, if we're going to do a sample problem, I think it's much better for your first time calculating the escape velocity to calculate the escape velocity of your own planet, Earth. So cross out Mars. We're going to replace it with Earth, and that is what you are going to submit for question 58A. Does that make sense? Okay. So for our sample problem, which is going to be question 58 modified, is find the escape velocity of Earth. I need to erase all this so I can write all it down. So let me just make sure everyone's caught up. Give me a thumbs up if you're ready to move on. All right. Nick, you need a second? Oh, you're good. Okay. So once again, this is going to be part of your homework that's due for today. So this is chapter 4, number 58, modified. Find the escape velocity of Earth. To do this, we're going to need to know the mass of Earth, 6 times 10 to the 24 kilograms. We're going to need to know the radius of the Earth, 6,400 kilometers. However, the escape velocity of Earth is an MKS formula. That means we need to convert our radius to meters. Yimmersey, I haven't picked on you in a while. Would you help me convert the 6,400 kilometers into meters using dimensional analysis?
Oh. You're gonna take the, which one is the 6,400 you said? The 6,400? Yeah, so you're gonna take 6,400 and take that and times it by division bar.
Excellent.
The kilometers will be in the bottom, and then the meter will be on the top.
Beautiful.
And then it's 1,000 meters per 1 kilometer.
Damn, you're good. You're no fun at all. Okay, and can you do this in your head?
It's gonna be,
I'll get you started. 6.4 times 10 to the what?
6 power.
That's right, because you've got 1, 2, 3, 4, 5, 6 places moved, all right? Pretty good, Yimmersey, I like it. Okay, we're ready to calculate the escape velocity of Earth. The escape velocity of dear old planet Earth, then, is the nice big neat square root of 2 times 7 times 10 to the minus 11, not minus 77, Adrian, minus 11 meters cubed per kilogram per second squared times the mass of the Earth, 6 times 10 to the 24 kilograms, divided by 6.4 million meters. Okay, this should be cakewalk compared to what you did for me earlier, so go ahead and punch that up. Hoping these clouds go away so I can try to see that comet. It's supposed to be clear by 6 p.m. That means I might actually get to see that comet tonight. You forgot to square root, Janabelle. Hit shift square root. I know. I'm like Mr. Wizard over here. Nick, something went very, very wrong. Can you punch it up again? Olivia, I don't like it. Something went very wrong. No. Jeez. Anyone? Oh, hey, Megan, you've got it. And Adrian, you've got it. Megan and Adrian have it. Makes me happy. Did you use my technique, Adrian? Yes. Okay, for the rest of you, try it one more time, and if not, I'll just show the whole class. You and me both, Adrian. I'm not gonna lie, I stayed up last night watching Cowboys and Aliens. That's how desperate I was. What were you gonna say, Adrian? Wait, you're muted.
I just said, hey, same.
Really? Wait, you watching that movie too?
Not that one.
Oh, something
but-
else. Oh yeah, okay. It was kind of dork. It was. I knew it was going to be bad going into it, but it wasn't as bad as I thought it was going to be. I actually didn't finish it. At some point, I was like, "This is fucking ridiculous." Yes, Nick. Nick, you have it. But I'm not sure. I'm not sure it was worth staying. You know, Olivia, you're not getting it. Okay. Here. Here. Why don't we? No. Okay. I don't know what's going wrong, but why don't you just watch me? Because maybe that'll be the best way to do it for those of you who are getting it wrong. So we're going to do the interior first and the square root at the end. So 2 times 7 exp negative 11 times 6 exp 24 divided by 6.4 exp6 then equals then shift square root. And that's what you ought to see. Yes, Olivia, you've got it. Janabelle, have you got it too? Yes, Andrew. Okay, Olivia, you got it? Yes, Ymercy. Okay, everyone's got it. Yay. So let's round it to something. Olivia, what should we round this to?
It should be in scientific notation, right?
Is it bigger than 1 million or less than 1 million?
Less than 1 million?
Then scientific notation is not required.
Okay.
But you can still round it.
Okay. Would I round the whole, like the number?
2
Would it be
sig
like
figs.
2 sig figs? Okay.
What is the number rounded to 2 sig figs? Does anyone understand that? Okay, Megan, tell us then. Butt in.
I will butt in. It's 11,456.4.
Whoa. That's, you just gave me 6 significant figures. I want 2.
11,000 then.
1.
Yeah, 11,000 what? Your answer is roughly 11,000. 11,000 what?
Meters?
Nah. Okay. Let's go
Oh,
to
no.
Megan, do you know?
Is it seconds?
No. Megan, let's go to unit jail and let's balance our units. What can I cancel out in this equation?
Meters?
You can cancel 1 meter with 3 meters. What does that leave behind?
2.
That leaves meters squared behind. What else can you cancel out?
That's it, right?
No, you have a kilogram that's on the top of the top and a kilogram that's on the bottom of the top.
Oh, then kilograms you can cancel out.
What do I have left over?
Seconds squared.
False. You have a meters squared up here too.
Oh, well, yeah. Sorry.
So what do you have?
So would the squared cancel out though, or no?
No, the squares don't cancel out, but what you have, Megan, is the square root of meters squared per second squared. Squares don't cancel out, but the square root can be distributed to both of these. The square root of meters squared over the square root of seconds squared. And the square root kills the square, leaving behind meters per second, which makes sense because this is an escape velocity. And MKS units of velocity, you may recall, are meters per second. That's how we balance our units. Hey, how many kilometers per second is that? Can you do that in your head?
11.
Yes. That's 11 kilometers per second. It's customary to convert escape velocities into kilometers per second. Did you know that at the current best ability of our rocket technology, we only have the fuel capabilities to accelerate rockets up to 10 meters per second? We should not be able to leave the surface of Earth at our current level of rocket technology. But there's a trick. If you think about it, you sit on a spinning, rotating Earth, right? And on a spinning, rotating Earth, you have a non-zero velocity through space. Okay, if you're at the North Pole, then you just kind of do this during a 24-hour period. You're not really traveling. But if you go anywhere south of the North Pole, you travel some circle's circumference in 24 hours, and that's a distance divided by a time, so you have a velocity. And it turns out the closer and closer you get to the equator, the faster your velocity, because you're traveling a bigger and bigger circle in the same 24-hour period. It turns out that somewhere right around the latitude of Florida in Cape Canaveral, your velocity through space is roughly 1 kilometer per second. So what they do to get astronauts into outer space, if you've ever seen a shuttle launch like that Dragon capsule launch that happened recently, I have a picture that I like. It's a shuttle launch that's seen from like some kind of cool military jet, like an F-15 or an F-14. I don't know. I'm not enough of a jet nerd to know. I should be. I mean, that stuff is cool. Oh yeah. Oh wow. This is cool. Here's a shuttle Discovery launch. I'll go with this picture instead because it was the first one to come up. After you launch a rocket into space, you go as far south in latitude as you can go, and you actually fire the rocket into the curvature of Earth. This is how crazy this stuff is. You basically fire the rocket into the Earth's rotation, and Earth's rotation gives you the last kilometer per second that you need to get up into outer space. This is why the shuttles always curve right, is because they're firing them into the direction of Earth's rotation. Pretty wild stuff. Any object that travels at 11 kilometers per second can leave the Earth. It does not depend upon the mass of the object. If I could take my magic marker here and chuck it at 11 kilometers per second, I could throw it into outer space. Is 11 kilometers per second fast, or is that slow? What do you think? Should we ask Google here? Let's do 11 kilometers per second to miles per hour, just to give you a sense of what that is. That's roughly 25,000 miles per hour. So if you could drive your motorcycle 25,000 miles per hour and launch off of a ramp, you too could go into outer space, okay? All right, make sure you submit that as part of your homework today. We're gonna change gears a little bit and we're gonna talk about something else. I need to erase. Hopefully there's no objections there. Okay, Megan, you were saying there was a thing I wanted to talk to you guys about. And that thing has to do with momentum. You'll remember that Newton's version of Kepler's second law had to do with something called the law of areas. And that states a planet sweeps out equal areas in equal intervals of time. Sometimes it's abbreviated as equal areas in equal times when we're feeling real lazy. And Newton discovered there was a reason for that. And the reason is an important issue in physics and astronomy. It's the conservation of angular momentum. And it occurs to me that you guys probably have no idea what that means unless you've taken a physics course. Angular momentum is not a concept you would. How many people have taken a physics course? Show of hands. Adrian has. I took one in high school. All right, so Adrian, you'll permit us the review. Let's talk a little bit. If you're going to learn about angular momentum, you have to start by first learning about something called linear momentum. So let me introduce you to some physics concepts. Linear momentum is an invented concept in physics, although there is a psychological effect of it too. We give it the letter P for historical reasons. And I like to think of linear momentum as the amount of oomph of a moving object. Now that's my own personal wacky definition to give you a touchy-feely sense. It's the amount of oomph that a moving object has, if that makes any sense. The real definition is that linear momentum is the product of some object's mass times its velocity. So usually you have some kind of particle. Here's a particle, and it travels through space. And if it has a velocity and it has a mass, it'll have a momentum. What's cool about momentum is that linear momentum is a conserved quantity in physics. And what a conserved quantity means is that the total momentum in a box or in a system of particles must remain constant. This is cool because it gives you special powers, the powers of prediction, and makes you a kind of Nostradamus of science that can figure out what will happen when objects bash into each other and collide with each other. For instance, probably one of the most classic forms where we study momentum is to think about like, well, you could do this. Ever see this toy before? Newton's Cradle. I have one in my office, but I forgot to take it with me. Let's just, I bet I could substitute a YouTube video since I didn't. It would have been cooler if I had the thing here. Newton's Cradle. Newton's Cradle can be surprising the first time you see it, because you're surprised that you can transfer the motion of one moving object through a bunch of stationary objects. But the idea is that this is a direct application of the conservation of momentum. Let's see if we can get the click-clacks going here. Oh, I hate the guitar music. The guitar music is terrible. Okay, anyways, I did want to hear the clicks, but why do people have to do that? You know, just the sound of the clicks would have been fine. All right. You can see what's happening here is momentum is being transferred from, well, I guess the original demo was just one ball through the three balls to the other one. Another classic demonstration of linear momentum could be if you've played a game of pool before, which I'm sure most of you have. You know that when you strike the 8-ball with the cue ball, usually what happens is the cue ball comes to rest and the 8-ball begins to move. Now, I got to tell you something. It's kind of cool. You can predict how collisions will occur because of the conservation of linear momentum. And there's kind of 3 different regimes of collision. In the first regime, the two particles are equal in mass. And that's the most interesting one, because if the particles are equal in mass, the first object will come to rest on the collision and transfer all of its momentum to the second particle, which begins to move. And you've seen that in Newton's cradle. You also see that in a game of pool. Another collision regime is that of a BB striking a bowling ball. If a BB strikes a bowling ball and it has a very low mass, you can use the equations of momentum to prove that the BB will just bounce off the bowling ball and the momentum will backscatter to the original particle and travel on its way. And the third scattering regime is where you have a BB getting struck by a bowling ball. In that case, the bowling ball becomes a snowplow and it picks up and just carries the BB along with it. And if the masses are a little more equal but not perfectly equal, you'll get something in between those 3. So those are your 3 extreme regimes of scattering. Why am I mentioning this? Knowing that momentum is momentum is a little bit more abstract than your average quantity in physics. A velocity is a very straightforward idea. Anyone who's traveled on a bike can understand velocity. Mass, have you ever picked up a brick? Have you ever picked up a rock? Then you understand mass, right? Momentum is a bit more abstract, and yet these are quantities that we understand intuitively. For instance, let's say that you found yourself in a supermarket parking garage, and you saw a runaway shopping carriage, and there was a baby in the shopping carriage, and it's traveling down the ramp at 5 meters per second. Now, you might be tempted to be a hero and jump in front of the shopping cart and save the baby. But suppose we put that baby in a school bus instead of a shopping cart. Even if the velocity was 5 meters per second, you would think twice about getting out in front of the school bus, because you know that not only does an object's velocity matter, but the mass that object has will influence your ability to stop it. A school bus carries more oomph than a shopping cart. However, momentum is a little bit more abstract than velocity or mass. And another thing that's abstract is rotation. In physics, every time you make something rotate, I don't want to say twist, but I guess I'm going to. You twist the concept a little bit, okay? You make it a little bit different than it was before. So while there is a concept of linear momentum, there is a separate but related concept called angular momentum, and that's a little bit more complicated. However, angular momentum plays a big role in astronomy, so it's worth us discussing. Introducing a concept known as angular momentum. In physics, in energy, in chemistry, and in engineering, we give angular momentum the symbol L. And angular momentum is defined as the product of an object's mass times its velocity times the radius. And so the mass and the velocity are just the normal momentum. The radius is the radius of orbit. Sometimes people might call it the moment arm or the radius of orbit, whatever. And usually your mass is traveling at some velocity, but in this case, it's a particle on a string, and it's kind of going around in a circle. Angular momentum, like its brother, linear momentum, is a conserved quantity in nature, but it can lead to some funky and surprising results. Allow me to demonstrate. Oh shoot, guys. Be with you later. I have a bicycle wheel here. And what's interesting is this is a rotational system. The edge of the wheel has mass. It has a radius of orbit, and it has a velocity if I give it a spin. The direction of angular momentum is kind of interesting. Rather than define it as going around in a circle, we define the direction of angular momentum as being directed along the axis of the rotation. Now, on this bicycle tire, I have a string attached to it, and when it's not rotating, if I hold the string, gravity will just kind of flop the tire over here. Not much I can do about that. But something interesting happens if I give it some angular momentum and I hold on to it. So let's try this. Let's give it a hell of a spin. Once I get it spinning, I can now hold the tire by the string, and instead of gravity being able to tip it over, it's going through this kind of crazy motion called precession. Watch this, I'll try to knock the tire over. I can't do it because of the conservation of angular momentum. Oh, there's an even more fun version of this, which may make me puke. Luckily, I had less drinks than usual last night. Let's put myself on this spinny stool, all right? Let's see if I can make myself rotate. I don't know if I'm gonna be able to do this or not. This is a cool variation of the demo. We're really fast, all right. Now I'm gonna try to, whoop. I can actually make myself rotate back and forth just by twisting the wheel. There's too much friction on this stool. It's better if it's really, if you have a, I should have greased that up with WD-40 before this, and you'd actually see me go flying around. I did this a couple of times and I fell off the stool and I got the spins in class. And that's when I realized I probably shouldn't do that demo anymore. Okay, so angular momentum is a surprising thing. It shocks you because it behaves in a counterintuitive way. Yet there are so many things in astronomy that depend upon this. Now, this isn't a perfect statement of what's going on. This is my own little twist on it. But I kind of think of it in the following way. So my quote about it would be, objects that start spinning want to stay spinning and in the same direction. This is what the fields, the real fields, are like. Oops, I'm a little too close now. All right. In any case, this is why in Kepler's second law, you can start to understand why the planet speeds up as it goes close to perihelion. Because the planet has angular momentum. When the planet is far from the sun, it has a large moment arm, and as the moment arm gets greater, the velocity shrinks. But as the distance between the planet and the sun gets smaller, the velocity has to speed up to account for that conservation of angular momentum. And the net result is what you see here. The planet moving faster near perihelion and slower at aphelion. Okay. That's all I'm going to say about angular momentum for now. Angular momentum plays a huge role throughout the solar system, so it's a concept that I wanted to make sure we addressed before I move on. Now we're going to shift and we're going to talk about energy, which is another concept that comes from Newton's laws of motion. So because momentum and angular momentum are defined in terms of masses and velocities and distances, they are naturally associated with Newton's laws of motion. A proper physics course would spend a lot of time exploring the relationship between Newton's laws and these concepts. Let's talk a little bit about energy. Energy is going to be our gateway drug that will help us transition from chapter 4, which concerns itself with gravity, and start getting us to think about concepts like light and atoms and heat, radiation. The fundamental definition of energy is very, very subtle, almost too subtle for us. So the technical definition is energy is a force multiplied through a distance. And while that is true, that's the most basic definition of energy. At your stage of development, it's not very helpful for you to understand what energy is all about. So let me instead tell you things that will be helpful. Energy, although abstract in its nature, is a conserved quantity. And physicists love conserved quantities because they give you the powers of prediction. The total energy in a box, the total energy in a thermos or an oven must always remain constant. So if some particles lose energy, others must gain them to compensate. Another thing about energy that makes it particularly beguiling, shall we say, is that energy takes various forms. And because these forms can seem so different from another, energy almost seems like a shape-shifting polymorph or something from science fiction that can take on different aspects. Usually the forms that energy can take fall under a number of different categories. There are potential energies. Potential energies are usually stored in a gravitational field or in some kind of force field. There are kinetic energies. Kinetic energies are usually associated with motion or moving objects. And there's even light. Light is kind of a unique form of energy that is a pure form of energy, neither exactly potential nor kinetic. Heat can kind of be associated with kinetic energy, so heat is another form too. But I'm going to start by introducing you to one of the forms called gravitational potential energy. And that's how you're going to get your first introduction. Olivia, give me a thumbs up when you're done, and I'm going to erase. You're good? Okay. So let's introduce us to gravitational potential energy. It is the energy stored in a gravitational field. And the typical setup for potential energy is you have the ground and you have a mass, m, suspended some height above the ground on Earth. Okay? If you set the situation up like so, the gravitational potential energy is defined as m times g times h. Do you guys remember what g represents here? What's little g?
Is that one gravity?
Well, gravity's too broad a statement because there are different constants associated with gravity. You need to be a little more specific, Adrian.
Like with a number?
Well, you could give me that too.
Isn't it like 9.8?
9.8. Well, we call it 10. 10 what? The units matter a lot. Shucks.
Meters per second?
Almost. Meters per second squared. This is not gravity. This is the local acceleration of Earth's gravity. It is an acceleration. So let's take a look. I've really made a mess of things here. Hold on, guys. Having cart issues. Here we go. This, my friends, is a 1 kilogram reference mass. And a few moments ago, you may have noticed me eating a granola bar. I had a Cascadian Farms protein bar, and I've given my muscles some energy. And now I am going to do work. I am going to make a 2-meter stick. All right, there's 2 meters right up there. And I'm going to take this 1 kilogram mass. I'm going to observe it sitting on the ground, and I'm going to lift it up in the field of Earth's gravity. I'm going to do violence against gravity. I'm going to fight gravity. Ready? So I'm going to pick it up, and I lift it up 2 meters above the ground. And there it is. I've created some potential energy. Where's the energy being stored? Can you see it? Where's the energy? Where's that energy hiding?
In the object?
It's not exactly in the object.
Is it like your hand? Are you holding it?
Say that?
Are you holding it? Because you're holding it as high up. Depending on.
Energy is kind of an abstract quantity. I want us to think about where is the energy hiding? What is it? Where is it? I want to taste it. I want to touch that energy.
In the height?
It's a little bit of what you said and a little bit of what Adrian said and a little bit what nobody said. It's in the entire system of the mass plus the height plus the ground. One way I could help further explain that I was trying to get this set up because I knew I might want it. Oh, it's so easy to. Hold on here. This is why my apartment is now a mess. Oh no! Oh no, there's a knot. Here we go. Megan, consider the spring. A spring is not gravitational potential energy, but electromechanical potential energy, but it's the same concept. In physics, there's a law called Hooke's law, which teaches us that a spring has a natural equilibrium point. And if you stretch a spring, it will experience a restoring force, and the strength of that force is proportional to how much you stretch. In other words, if I stretch this spring, I'm stretching a force through a distance, and I'm storing potential energy. And it's clear that here the potential energy is stored in all of the coils of the spring. And if I release my hands, then whoosh, the spring will return to equilibrium. But you can see that the energy is being stored in all of the coils of the spring. The same is true with my 1 kilogram test mass, except here the spring is invisible because gravity is invisible. And yet, I assert to you, without dropping it on my toe, that if I were to release this thing, whoosh, gravity would snap it back to Earth with the same enthusiasm that it snaps that spring back. In other words, it is the system of me holding the mass apart from the Earth and the fact that Earth wants to rip it out of my hand. That's where the energy is being stored. And I can do things with this energy. I can take this stored potential energy and I can bring it over to a little village in Afghanistan and I can release it and drop it on some unsuspecting villagers, and that perhaps would be a dubious use of potential energy, but is one that happens all the time. Why don't we instead calculate the magnitude of our potential energy, okay? We know all of the numbers involved in the little exercise that you just saw there. We know that in my example, the mass was 1 kilogram. Little g is 10 meters per second squared, and the height is 2 meters. I'm going to do the hard stuff, which is 1 times 10 times 2. That gives me, oh, I'm sorry, yeah, that gives me 20. Can you guys tell me what the units of energy are?
Kilograms per second squared.
What happened to the meters?
They canceled. Oh, no, they didn't.
This meter is actually on the top, isn't it? If you are not explicitly in the bottom, you are on the top. So try again, Megan, if that was your voice I heard.
It was kilograms per meter over second squared.
Also not correct. Per meter means meter is on the bottom. I do not see any meters on the bottom. I also see 2, not 1 meters. Try again.
Kilograms times meters over second squared.
Almost. There are 2 meters, not 1. So,
Kilograms meters squared over second squared.
wait, say it one more time.
Kilograms times meter squared over second squared.
That's correct. Or a more elegant way to say it is kilogram meters squared per second squared. Those are your units of energy. Now, You can see that kilogram meters squared per second squared is kind of a mouthful. And it's actually kind of complicated to think about. Like, I understand what kilograms are, and I understand what a meter in a second is, but a kilogram meter squared per second squared, that's just downright confusing. And this could be a good time for us to hide our confusion, to sweep our confusion dust bunnies right under the rug and invent a new unit that will hide our ignorance. We will call this 20 joules worth of energy, where I have introduced a new unit of energy in the NKS system. 1 joule is defined as 1 kilogram meters squared per second squared. You can take that as the definition of the joule. I have a sample problem, some other stuff for us to do, but maybe this would be a good time for us to pause. You guys want to do a little break now? Megan was like, peace, I'm out. She's just vaporized. Okay, that's fine. All right, let's return at 10 past 2. We'll give ourselves a luxury break, okay? 10 past 2, we resume. I'll see you then. Hi, everyone. Shall we get back to it? Who's with me? Olivia, what's up? Megan, all right. What do you say we talk about units of energy? Let's have some fun. So, energy takes many forms, and it also has many different units. The first unit of energy that you were introduced to is the MKS system of units, the joule, defined as 1 kilogram meters squared per second squared. But there are other units of energy as well. In the centimeter gram second scale, they call units of energy ergs, but we're never going to use those, so I won't bother writing it down. How about if you pay your electric bill? Ever check out what you're paying for there on the electric bill? I always get the sticker that says, shame on you, Brendan. You used more energy than your neighbors. Does anyone actually end up on the right side of that? Do you ever find out that you use less energy than your neighbors? I always seem to be using more. Maybe I'm a wasteful consumer of energy. Well, no one pays their electric bill around here? When you do so, you pay for it in kilowatt hours. That's a kilowatt times an hour. In your gas bill, you pay for therms, which I believe are British thermal units. You'll sometimes see air conditioners and heaters rated in BTUs, British thermal units. How about in the imperial system of units? You know, like our English style units. Do you guys know what it's called, the unit? Ever heard of this one? A calorie. Ever heard of calories before? Those are imperial units of energy. 1 calorie is roughly 4.2 joules. Now, for some reason, food calories are actually kilocalories. Or 4,200 joules. For some reason, the FDA doesn't like to put kilocalories on food packaging, maybe because they don't want us to sound like those snobby European friends that we have. I don't know. For some reason, they decide to rename the kilocalorie the calorie, which leads to hideous confusion between the real calorie and the food calorie. Food calories are done with a capital C, and real calories are done with a lowercase c to help that. I'm nibbling on a Cascadian Farms granola bar. I wonder how many calories this has. Whoa! 240. That is a very naughty granola bar. I wonder if a granola bar has 240 calories. That means I'm going to have to work that stuff off after class by doing some exercise. But I don't see any weights around here. I'm going to need an exercise appropriate for a wimpy astronomer, such as myself. So I'm going to invent an exercise regime called the 1 kilogram squat. What I'll do is I'll start with the kilogram on the floor, and I'll pick it up, and I'll lift it 2 meters over my head, and I will repeat. How many joules of energy will it take to do this exercise? So imagine I wanted to do an exercise, and I'm going to define it as a 1 kilogram squat. How many joules will I use up doing a 1 kilogram squat? See previous calculation, 1 page up in your notes. We computed this before tea break. How many joules are in a 1 kilogram squat?
20.
Right. That's what we calculated before. Who said that? Yimmersey. Do you think you could help me solve a problem? Because I want to solve a little problem here. The question I'd like to work out is, how many 1 kilogram squats do I need to do to burn off 1 granola bar? Yimmersey, how would I solve such a problem?
Do you know the calories for the granola bar?
Right there. I was thinking this is like a job for dimensional analysis, don't you?
Yeah.
So let's use our steps of dimensional analysis to work our way through this. What's the first step?
Let me get that. Write down the number to convert with the unit.
All right, so what should I write down?
You're trying to find out how many kilograms, so you will put 1 kilogram.
No. I'm not trying to figure out how many kilograms. I'm trying to figure out how many kilogram squats I need to get rid of 240 calories.
All right, so you will put 1 kilogram squat.
No, I already know 1 kilogram squat is 20 joules.
Okay.
I'm trying to figure out how many kilogram squats are equivalent to 240 calories. Do you see what I'm saying? 1 kilogram squat is not the number you are trying to convert here. That's what you're trying to convert into, and it's an unknown number of kilogram squats. Did I lose you? Huh?
240 calories.
That's what you want to start with, because that's what we're trying to convert. All right, what should I do next?
Multiplied by division bar.
Fine. What should I do next?
Calories in the bottom.
And
Kilogram squat on the top.
do you have a conversion from calories to kilogram squats? I don't think you do. That won't work.
Okay.
Are you using joules?
I don't know. Are we?
I think so.
Okay. Is that your really weird way, Adrian, of saying we should put joules on the top?
Yes.
Okay. I like that because you do have a conversion from calories to joules, don't you, Adrian? What's the conversion?
4.2 joules to a calorie.
Ah, you have been bamboozled by the FDA. The FDA, in its attempts to make things more understandable, has actually made them more confusing. You have confused yourself. These are not British calories. These are food FDA calories.
Wouldn't it be 4,200 joules?
That's right, because this is actually a kilocalorie. Okay, now what do I do? Guys, I'm getting lost here. I'm getting confused. I need your help. I just need to know how much exercise I need to do to atone for my candy bar sins.
You take the answer of that and divide it by 20 joules.
Why don't we keep doing dimensional analysis, Megan?
Okay.
I'm not saying you're wrong. I'm just saying I want to do dimensional analysis. Units?
Would it be 1 kilogram squat at the top and then 20 joules on the bottom?
Right. We're going from joules into kilogram squats. 1 kilogram squat is 20 joules. Okay. Punch them up, guys. Tell me what I get.
$50,400 joules.
50,400. Like this? Wait, joules? Joules aren't even a unit here. We canceled out joules.
Kilogram squats.
Yeah. Holy shit. Maybe that's where my COVID-15 came from, as they say. Maybe that's what's up. Maybe I shouldn't have been eating that candy bar because now I'm on the hook for 50,000 squats. Do you guys think I could do 50,000 squats? What do you think? Oh, ye of little faith. I wonder how many, If I did 1 squat per second, that would take me 50,400 seconds. That would take me 840 minutes or 14 hours. That'd be 14 hours of squats. Damn, there's a lot of energy in food, ain't there? I wasn't anticipating that. Maybe I'll just put this over here and I won't finish it. Now that I've thought better my dietary habits. We're not going to be pushing squats or kilograms around, but we are going to go inside the world of atoms. And there we have to lift electrons in the potential energy field of an atom. When you deal with really tiny things like atoms, it can be sometimes helpful to introduce a tiny unit of energy, a tiny unit of energy that's used when we deal with either light or with atoms. Let me introduce to you a weird one called the electron volt. One EV, as the physicists say, is 1.6 times 10 to the minus 19 joules. That's a conversion that we'll need in our homeworks going forward. Let me tell you about some other forms of energy. Up to now, we've mostly discussed stored energy, like the energy that's stored in a mass suspended above the ground, or in the energy that's stored in my gut after I eat too many candy bars. Here's another form of energy, legendary photograph from the MIT professor who did the milk drop experiments. Doc Edgerton took this photo. This is a Doc Edgerton photo of a bullet rupturing an apple. Clearly, there is an energy contained in a moving object that has mass. One way to look at it is it takes a certain amount of energy to accelerate and get a particle moving. And we can define that energy as the kinetic energy. Kinetic energy, put simply, is the energy of a moving object. It's got a value of 1/2 mv squared. A bullet, well, I guess it depends upon what type of bullet you're going to use. You know, I don't know if anyone has been in the armed services and knows these kinds of things. Usually soldiers do. Mass of a bullet, I guess it depends what kind of bullet you have. A bullet can range between 0.2 and 0.02 and 0.04 kilograms. So we'll use 0.03. The speed of a bullet is usually around the speed of sound, 300 meters per second. Oh, wow. A muzzle velocity of 550 meters per second. Wow. So let's imagine we have a bullet whose mass is 0.04. Was that kilograms? That had to be. Yeah. So 0.04 kilograms and a velocity of 500 meters per second. the kinetic energy of this hypothetical bullet wow, might be 5,000 joules. How does that compare to my 1 kilogram squat? That's 250 times the energy of one. Do you know what that means? Getting hit with a bullet is like having 250 kilograms dropped on your head. Isn't that messed up? 250 kilograms dropped on your head. You know, I can remember a couple of years back, there was this horrible terrorist shooting in Paris. And all these poor kids who were out at a nightclub got shot by some armed lunatics. And it was super sad. I don't even know why I'm getting into it now. It's kind of depressing. But I watched an interview with this French guy, this Parisian dude who had gotten struck in the arm. And you figure, oh, you get shot in the arm, you're not going to die, you'll live, you get patched up, whatever. That's how they make it look in the movies. But he was in so much pain after the shooting, and his arm was like permanently messed up. And he said this thing that I thought was kind of profound to think about. He was like, you cannot understand the violence and the damage that a bullet does to the body until you've been struck by one. It just completely shatters you. It shatters your bones. It was kind of a gruesome thing to think about, but maybe an important thing to think about. There's a lot of energy contained in a moving bullet, which I guess is the point, to hurt people. Anyways, maybe we could think of a more peaceful use of our kinetic energy. Let's have a happy note. Oh, here's a peaceful application of kinetic energy. Maybe we could use the moving water molecules in a river to twist this turbine, and then I won't have to pay Narragansett Electric if I want to play Nintendo Switch. I could use this turning water mill to generate a current of electricity by rotating a magnet, and then I'd have free electricity and I wouldn't have to pay anymore. That would be a nice use of kinetic energy. Kinetic energies and potential energies fall under there are a lot of different types of energies. Light is a form of energy that I'll get into by the end of this lecture. Energy is also intimately related to the difference between temperature and heat. And that, I think, is our next discussion. The reason why is we're going to think a lot about temperature in this class because it turns out that the astronomical objects we're going to study have a variety of temperatures, and it affects how they behave, and it also affects what type of radiation or light they give off. And as you know, astronomers love light because that's how we study outer space. So let's have a little discussion here about the difference between temperature versus heat. And for fun, let's start by considering the temperature at which you cook a turkey on Thanksgiving dinner, or Thanksgiving Day, I guess I should say. Suppose we were to get together for Thanksgiving and we were to make ourselves some turkey. What temperature should I roast this thing at? Who's cooked a turkey before?
$350.
Okay. And that's in the Fahrenheit system, right?
Yeah.
350 degrees Fahrenheit. Let's say we need some extra turkey. Let's also get a big pot out and let's boil some turkey. So we can have some boiled turkey along with our oven roasted turkey. What temperature do I boil water at? Does anyone know the temperature of boiling water?
100 degrees Celsius. Celsius, but I don't think that's going to help us in Fahrenheit.
Yeah, we'll talk about Celsius too. Obviously, we're going to get into all that. I'm glad you at least know it in some temperature system, Adrian. Oh, you're hiding from me. I see. Okay. All right. I was looking through your face. No one knows the temperature of boiling water in Fahrenheit? Do you guys know the temperature of what? Oh yeah?
212.
Who said that?
Me, Nick.
Oh, Nick. Hey, way to go, buddy. Yes. 212 degrees Fahrenheit. Ding, turkey's done. Okay, now Nick, let's say I can't find my oven mitts, all right? But we got to make the turkey. We got to get it out of the water. We got to get it out of the oven. We got to serve it to the class. One of us is going to have to put their bare hand into the 350-degree oven real quick and pull out the turkey. And the other person's going to have to put their bare hand into the boiling pot of water real quick and pull out the turkey. Which job do you want?
I'll put my hand in the oven.
I don't know, Nick. That sounds crazy because the oven's at a higher temperature. So wouldn't you get a worse burn putting your hand in the oven than you would in the boiling water?
No, because I'm not touching anything like I would be touching the water.
I disagree, my friend. You are always touching something. Do you see your hand here? It is not exposed to the vacuum of space. Your hand is touching air always. And I would assert to you, Nick, that when you put your hand into the oven, your hand is now in direct contact with air molecules that are at a temperature of 350 degrees Fahrenheit. So I want to know, Nick, why is it okay to touch air at 350 degrees Fahrenheit, but it's not okay to touch water at 212 degrees Fahrenheit?
Air stores heat. Water stores heat.
But air also stores heat, correct? You're not wrong, Janabelle. That's where I'm going with this.
Is it because you can move the air? No, because you can move water when you put your hand in.
Yeah, exactly. Actually, Janabelle was getting closer to, shall we say, warmer. Janabelle was getting warmer. So say that again, Janabelle, because I think you kind of said the right thing, but I want to flush the concept out.
Unlike air, water condenses heat, like it packs more heat in it.
You can't say unlike air because air also can store heat.
Okay.
But you can say that there's more heat contained in the water.
Yes. Mm-hmm.
So here we have a weird situation then, Janabelle. This is at a higher temperature than this, but this contains more heat than that, all right? This is the difference between the two. Let's talk about them. Heat, properly defined, is a transfer of energy from point A to point B. Heat is a transfer of energy from point A to point B. Point A could be the air in the oven, and point B could be the delicious roasted turkey. Energy is being transported. In nature, there are only 3 modes of energy transport, sometimes also called the 3 modes of heat transport. It's kind of like a general science thing that you ought to know about. The 3 modes of heat transport are convection, conduction, and radiation. As time goes on in this class, I will train you to differentiate between convection, conduction, and radiation. But from now on, I want to tell you that heat, or not from now on, for now, for the moment, heat is a transfer of energy, and like energy everywhere, it's measured in joules. In fact, if I were to be mathematical about it, heat is a delta energy. But it's an energy nonetheless. You know, if you subtract 5 oranges minus 2 oranges, you get 3 oranges. The units of orange are the same whether you're dealing with a change in oranges or whether you're dealing with a total number of oranges. So delta energies are also measured in joules. Let's differentiate that with temperature. But first, I'd like to introduce you guys to a friend of mine, a friend known as the ideal gas. Let's take a look at what those molecules in your oven look like. Oh, crapola. You know, this, I have another slideshow, which over time has grown superior. So I will access that. Come on. Slide 22. These could be the molecules of air that are in your oven, a mixture of nitrogen and oxygen. The blue pellets represent nitrogen molecules and the red pellets represent oxygen molecules. Each one is kind of like a little bullet or a little BB. And all these little bullets contain kinetic energy, just like the bullet from a gun does. They have a small but significant mass. They have a rapid velocity. And as they bop around, they transmit energy and momentum to their neighboring particles. And if they're in contact with the walls of a container, they will even transmit energy to the walls of their container. If you try to follow one particle around, like one of these red particles, it's kind of an irritating task because the particle is moving around, but it's also colliding with its neighbors. And every collision exchanges energy and momentum, meaning sometimes the particle is moving fast and sometimes the particle is moving slow. In other words, it doesn't really make sense to talk about the energy of a single particle because it changes so much. But we could talk about the average kinetic energy of those particles. And that should remain constant in the box. That's what we mean by temperature. Temperature is the average kinetic energy in a system of particles. And those particles could be in a gas, liquid, solid phase, hell, even in a plasma phase, or even the Bose-Einstein condensate phase, which most of you have never heard of before. And by kinetic energy, I mean the good old-fashioned 1/2 mv squared. Now, because the masses of the molecules do not often change, I now want to tell you guys a useful lie. A useful lie, which is perhaps more useful than the truth. Lies are often more useful than the truth. Most of us know this intuitively. So here's another one for you. Temperature is kind of like the speed of the particles. That's not true, but it's close to true, and it's the real feel true. You know, like there's the temperature and then there's the real feels. The real feels is that temperature is the speed of the particles. So class, in which scenario are the particles traveling at a faster speed? In the water or in the oven?
Water.
False. The water is at a lower temperature, therefore the water has a lower kinetic energy per particle, therefore the particles are traveling slower. Why am I getting burned worse by water when the particles are traveling slower then? Does anyone understand me / care?
The particles can spend more time in one spot.
Nick, that was not perfectly said. It's not about them spending time in one spot. It's got something to do with this picture here. The particles are traveling faster in the air than the water, but the water burns me more. Why?
Because they're like compacted like a chain structure, like they're together.
Is that you, Janabelle?
Yeah, it's like if you was to wave your hand right now in the air, you're gonna feel air because that wasn't a good one. Never mind.
No, but
I'm
you,
just
yeah, you were. It's hard to talk about these things, which is why we need to practice. But you did a decent job. Let's pretend your hand is a circle, right?
Mhm.
If you put your hand into the liquid, the particles start to slam into the walls of your hand, and that's why you get burned. The particles are moving slower in the liquid because it's cooler, but there are more particles slamming into your hand per second, and therefore more heat is transferred. Here, the particles might be traveling faster, right? But there's fewer of them bumping into your hand per unit time. So heat is about the amount of energy that that substance can give you, whereas temperature kind of tells you how fast the particles are moving around. This can be really awkward because if you go into outer space, there's very few gas particles. But those gas particles that you find are traveling very fast. So the temperature of gases in space are often really high, sometimes in the millions of degrees. But if you took your hand out of your space glove, it would not feel warm in space because your feeling of heat is about your feeling of temperature is about how much heat is being transferred. You know what I mean? I don't know. Okay, I tried. In any case, there's 3 temperature scales, and we should discuss them all. I think I'm going to do this in atoms before I stop. So let me explain what we have left to do. I'm going to give you the temperature scales, and I'm going to give you a little breakdown of atoms so that I can test you on it. Then I'll talk about the test, and we'll break by 3:30. Is that a plan? I'll get done sooner if I can, but I don't know. Let me show you a little slide that you can pay attention to in my chapter 4 notes. This is what we're going to reproduce on the board. It's just some sort of famous, some different temperatures that might be helpful for us. We're going to be using 3 different temperature scales and a little chart that will help you differentiate between the 3, excuse me. Let's make a little chart together. Going forward in this class, students, as I've mentioned before, if you're ever at CVS or any job lot or whatever, grab yourself a little $2, actually this isn't even $2, this is probably 50 cents. Get a 50-cent ruler, they're gonna come in handy, okay? Just a good thing for a student to have in their apartment. All right, let's make our temperature scales here. So we're going to study 3 different temperature scales. The first column is for the substance. Then we'll do degrees Fahrenheit, degrees Celsius. And then I want to introduce to you guys, if you haven't heard of it before, the Kelvin scale, which is somewhat similar to Celsius. At the top of the deck, we'll do boiling water, which Nick reminded us is 212 degrees Fahrenheit, which Adrian reminded us is 100 degrees Celsius. Save the Kelvin for last. Next up, let's not forget the temperature of a human to 2 sig figs, 99 degrees Fahrenheit, maybe 37 degrees Celsius. Room temperature is around 68 degrees Fahrenheit, or roughly 20 degrees Celsius. What's the temperature of freezing water in the Fahrenheit system?
32.
And in Celsius?
0.
And we're going to do one more. You know, we've been measuring temperature longer than we knew what the hell temperature even was. In the olden days, people just thought of temperature as I feel hot or I feel cold. And they put a human body around 100 and boiling water around 200. And that's how the Fahrenheit scale was developed, which is nuts because you're using 2 different thermometric substances to define temperature. Celsius improved on the game by saying, what if we just used water and only water? And what if we set it up so that water freezes at 0 Celsius and boils at 100 Celsius? And that will be cool. And everyone liked the Celsius scale. But yet, over time, people began investigating the nature of gases and what it meant to measure temperature. And they began to figure out that what they were measuring was the speed of the particles. And as they cooled a substance down, as they rid it of kinetic energy, the particles began to move slower and slower and slower. And although they had trouble getting there, they realized that there was some limiting temperature, a low point at which all of the molecular motion would stop. And that's when they would reach, what do we call that, students? The absolutely lowest temperature at which all molecular motion ceases. Have you heard of this?
Isn't that absolute 0?
Oh yeah, absolute 0. And absolute 0 is sort of nature being pushed to its absolute extremes. Absolute 0 occurs at negative 460 degrees Fahrenheit, or negative 273 degrees Celsius. Now, nature behaves very weirdly as you get close to absolute 0. We've never actually achieved it in a laboratory, but we've gotten into 1/10,000,000th of a Celsius degree of absolute 0, which is pretty extraordinary. Kelvin's whole concept, Lord Kelvin, said, you know what? I like the Celsius scale. I think it works. But what I think is silly is I don't think we should have negative temperatures because temperature is inherently a positive quantity. It starts when the particles are 0, and as they move faster, we'll increase them. So he shifted the 0 point of Celsius down here, but he left every other part of it the same. So now in the Kelvin scale, by the way, we do not use degrees when we specify Kelvin. Freezing temperature of water at room pressure is 273 Kelvin. Boiling water is 373 Kelvin. A human is 310 Kelvin. Room temperature is 293 Kelvin. Obviously, I'm telling you all this because Kelvin is the official MKS unit of temperature that's used in most scientific applications. Scientists use Kelvin as a more natural unit. Okay. One more module to go. Having done all of this, we are now ready to discuss atoms, which will be our gateway drug to talking about light. I want to squeeze atoms in before we stop. I know it takes some stamina here. Here's a picture. Do you guys know what this is? This is the Bohr model of the atom. What are these things? How many people here have taken a chemistry class? Can I see a show of hands?
Biology.
Maybe at some point. All right. I'm not asking if you're good at chemistry. I'm just asking if you've been exposed to chemistry. Okay. So Adrian, tell us about these particles here.
All three of them?
Why not?
All right. Well, the ones on the outside, the blue ones, are electrons. They carry a slight negative charge.
Correct.
The red ones in the nucleus are protons. They carry I believe they're a slightly stronger positive, but they usually
No,
can't clear out.
the positive charge in a proton is perfectly equivalent but opposite to the negative charge of the electron.
Right.
Okay.
And the third one is a neutron, and it has no charge.
Correct. Now, what I want to find out from you is, Adrian, I just want to find out where the bottom of the well is, where I break you. So it looks like the electrons are orbiting around the nucleus. What causes the electrons to orbit around the nucleus? What's responsible for that?
I don't quite remember because this was 10th grade. So
Okay. Does anyone know? I'm just.
Is it like when you put two batteries together? Since the center has positive.
Yes. Actually, that's pretty good, Janabel. It's related to the same force that controls batteries, but also magnets. It's a new force of nature called electromagnetism, okay? Basically, if I asked you guys what makes Earth orbit the sun, most of you would say gravity. If I ask you what makes electrons orbit the nucleus, you'll say electromagnetism. And that's related to charge. So that helps me. Let me give you guys some concrete notes to digest here, okay? Let's talk about atoms. First thing I'll say is atoms are held together by a new force called electromagnetism. Electromagnetism is the same, is another fundamental force like gravity, and it governs both currents of electricity and also magnets and protons and electrons. Electromagnetism works on the principle of charge. And to consider our three particles, we have a positively charged proton, a neutral particle called a neutron, and drawn much smaller, a negative charge called an electron. Their charges and their masses are not the same. If I were to ask you about the mass of these, relative to the mass of an electron, if I say the mass of electron is 1 electron mass units, the neutron and the proton are about the same mass, and they're 2,000 times more massive than the electron. I'll represent it by a blue m sub e. So the actual mass of an electron is 9 times 10 to the negative 31 kilograms, but I don't have time for all that. That's weird because nature makes these particles big and fat, and this particle is little and tiny. But they are not like that when it comes to charge. Charge governs electromagnetism. A proton has a charge of +1, an electron has a charge of -1, and a neutron has a charge of 0. And it's kind of berserk because the positiviness of the proton might be balanced by the negativiness of the electron, but they are weirdly asymmetrical in terms of their mass. How can nature pack so much negativity into such a little particle? I don't know. Nature does weird things. In fact, it's going to turn out that later, when we talk about nuclear reactions, it's possible for nature to do the opposite. She sometimes makes little tiny particles that are positively charged, called positrons, and sometimes makes big, fat, negatively charged particles called antiprotons. These are antimatter particles. But y'all ain't ready for that yet. You haven't earned it. Let's discuss the Bohr model of the atom. And by way of discussing the Bohr model, we'll focus on a famous atom that you guys should be aware of called helium. This is what helium looks like. It has 2 protons and 2 neutrons, and it has 2 electrons. And you guys know that these particles are called, we better write it down just in case, protons, neutrons, shit. I ran out of room. Sometimes I'm going to introduce some new vocabulary. We call these particles nucleons. Nucleons are protons or neutrons. Sometimes you don't want to specify whether it's protons or neutrons, but you just want to talk about all the particles in the nucleus, and that's nucleons. Okay, I'm now going to define some terms for you. The atomic number, which I will call A, is the number of protons in your atom. What's important about the atomic number is that it defines the atom or the element. Sometimes it can get confusing when you mess with nucleons, which atom you're talking about. By defining the atom as the number of protons, you keep your brain straight. Let's introduce you to a friend of mine called the periodic table of the elements. These are all the atoms that we know exists in nature. And the atomic number can be seen in the upper left-hand corner of each atom. It's the most important. For instance, silicon has 14 protons. Aluminum has 13 protons, so forth and so on. Atoms can vary in their number of neutrons. This is why we need another term called the mass number. The mass number M is the number of nucleons in your atom. And that means it's the number of protons plus the number of neutrons. What's important about the mass number is that the mass number defines the isotope. Oh, here we go again with our fancy vocabulary terms. It defines the isotope. And the isotope just basically means same number of protons, different number of neutrons. Most atoms, which are held by electromagnetism, are electrically neutral. And electrically neutral means they have equal numbers of protons and electrons. Why are most atoms electrically neutral? Because electromagnetism is an incredibly violent and destructive force in comparison to gravity. Electromagnetism is powerful and mean. And when you build up even small amounts of charge, nature tends to get very pissed off at you and will do dramatic things to solve the problem. It wants to balance its electrons and its protons. This is an example of what happens in nature when you don't balance charges. Nature will suck a stream of electrons off the ground and pump them into a cloud because that cloud has lost too much negative charge in its rubbings against the air. Sometimes charges do become imbalanced, and that's when you get ions or ionized particles. An ion is when you either remove or in some cases add electrons. When you do so, you create a charged gas called a plasma. Or in a single particle, you'd call it an ion. A plasma is a collection of ions. Wow, I did that fast. We should probably just do a little test to make sure you guys understand all this. Give me a thumbs up if you've got these notes. I want to know when I can erase. All right, everyone's with me. Cool. All right, here I go. I've got one more little page of notes for you, and then we're done. Let's play a game. This game, notice the festive lights appear when it's time to play a game. Okay, so let's build an atom. Okay. The first atom has an atomic number of 1, a mass number of 1, and is electrically neutral. Let's pick a victim. Adrian, would you like to go? Tell me how to make this atom.
So you would, with the Bohr model, you would put 1 proton and 1 neutron in the center to make the nucleus.
Hold on a second. M, the mass number, is your number of nucleons. How do we define nucleons?
Sorry, just 1 proton.
Yeah, you've used up your 1 nucleon, haven't you?
Yeah.
Okay. And what else were you saying?
And then you put 1 ring in the electron cloud and add an electron to it, and that's it.
Do you know the name of this atom?
Hydrogen.
This is not, this is hydrogen. You're correct. All right, Adrian, I'm gonna keep pushing you, okay?
All right.
This is not simply hydrogen. This is a unique isotope of hydrogen. Do you know the name of this isotope of hydrogen?
I think it would be, I want to say hydrogen 1 because that's how many,
You could call it hydrogen 1, but it actually has a proper name, like Frank. Except it's not Frank.
I don't think I know.
All right. It's called protium. Protium is the name of this isotope. Now you know. Okay. Someone besides Adrian is going to play with me now. Let's build another atom. This atom has an atomic number of 1, a mass number of 2, and is also electrically neutral. Andrew, I just haven't heard enough of your voice today. You feel like you're up to the task?
Why not?
All right. Build me an atom. It's got an atomic number of 1, mass number of 2, and is electrically neutral.
They're gonna have a positive in the middle,
1 proton, yes.
and then 1 neutron.
Very good, because we need 2 nucleons now. Excellent. Anything else?
And then a ring around it.
1 electron.
Yep.
Do you know what the name of this atom is?
I should know it, but I forgot.
Anyone? Adrian.
Isn't that still hydrogen?
Yes, very good, because the atomic number defines the atom. Since the atomic number is the same, it is still hydrogen. But of course, Adrian, this is a different isotope of hydrogen. Do you know what it's called?
I think that would be hydrogen.
You could call it hydrogen too, but once again, it also has a proper name, like Frank, except not Frank.
I don't think we learned those when I was in chem.
I guess it doesn't come up right away. This is probably the most famous isotope. These 2 atoms are isotopes of each other. Write that down. Because they have the same number of protons, but a different number of neutrons. This is the most famous isotope in nature, deuterium. Before we end our class today, let me tell you why this is important. Let's take a little trip to outer space together. Let's go somewhere fun. Let's go to the Eagle Nebula. And we're going to fly through the Eagle Nebula in our cosmic vacuum cleaner spaceship. This spaceship is a giant vacuum cleaner for atoms, and it can suck up. Oh man, this is a big picture, but why you make you so small? On Control plus. Oh, that's why. There we go. Look at this beauty. Oh, that's a very high resolution picture. I'm going to take my little spaceship. They have a little spaceship sticker. Let's make it an arrow-shaped spaceship. And I'm going to fly through the Eagle Nebula. And as I do so, I'm going to slurp up atoms, and I'm going to count them and sift them into boxes. If I do this, I will discover that 9 out of every 10 atoms is a hydrogen, and the 10th one is a helium. That's mostly what this is made out of, hydrogen and helium. Let's throw the heliums in the garbage because helium's boring, and let's focus on those hydrogens. And let's keep building up a big, big box of hydrogen. I would discover that in nature, for every 1 protium atom, sorry, let's try that again. I would have to count through 6,000 normal protium hydrogens to get to 1 deuterium. I would find that not only in the Eagle Nebula, But even if I sifted through the water molecules in this cup of coffee, I would also discover that 1 out of every 6,000 was not H2O, but was HDO with the deuterium stuck to it. This is what is known in physics as the cosmic abundance of deuterium. And it plays a huge role in many branches of science, especially in astronomy. This deuterium has been around since the beginning of time. And I know that because the Eagle Nebula has been around since the beginning of time. And that means that somehow the Big Bang was responsible for creating this deuterium ratio. 1 deuterium for every naturally 6,000 occurring hydrogens. Isotopes occur naturally in nature for a variety of different reasons. Sometimes it has to do with the types of fusion taking place inside of stars. Sometimes it has to do with weird reactions in chemistry. Well, nuclear chemistry anyways. But in the case of deuterium, it has to do with leftover conditions from the Big Bang. When people perform experiments, when they measure the atmospheric composition of Mars, or when they study the water ice in comets, they often sample the abundance of deuterium to try to figure out if the hydrogen that's been there has been around since the beginning of time, or if it has been morphed or changed in some way. And they use changes in these isotopes to tell a story about what happened to comets over time. It's very cool. You're going to see some of that coming up in our class. Okay. That's all about what we have time for, or probably what we can handle today. You've learned quite a bit. Let's talk about the test, the format, what we're going to do. The single biggest thing that we need to talk about is how we are going to approach the test. The way we're going to approach the test is we are going to meet at our normal office hours time of 10 o'clock. And I'm going to give you guys sample problems similar to the ones that are in the test. Just like in a normal office hours where we work out homework problems together, I will run us through how to do problems that are similar to the ones on the test, and that will train you for the test you're about to take. Everyone likes that idea, right? Because if you don't, I'm happy to sleep until noon and just drop it on your heads. But I think you'd like a trial run first. You'd like to kind of go over the problems. That sound helpful? All right. Also, so we'll meet for our normal office hour times. Oh yeah, heck yes, says Megan. All right, we like to hear that. We'll meet at our normal time of 10-ish. Hopefully it won't be quite as late today. Today I screwed up and I posted the link to the announcements. That was a mess up, okay. But close to 10, we'll do our office hours. And I'll run through some sample problems with you. During the test is not going to be in the form that you saw, Janabelle. It should be, if I finish entering all the questions, you'll be able to click the boxes, and it'll be like an application inside Blackboard. So you'll launch the test, and I'm hoping, I've never done it before, so you guys are going to be my guinea pigs. But I'm hoping what happens is when you launch the test, it'll display the question, you click A, B, C, D, E, and then you move through the questions that way. You should be able to go forward and back. You'll have about 3 hours to do the test, from about 12 to 3. If you need a little extra time, that's fine. But by 4 o'clock, I'm going to start, well, I'm going to just log out. All right. But while we're taking the test, my recommendation is you guys might want to ask me questions, and you might even want to ask me for a hint if you get stumped. So what do you say we do a normal, we'll be in the Zoom meeting anyways, right? Why don't we all stay logged into Zoom, but just mute ourselves, okay? Hell, you can even mute your video if you want to. It's your choice, okay? And I'll be muted and you'll be muted, but my computer will be on my desk over there, and I'll just be doing stuff around my apartment. Maybe I'll be grading and doing something productive. Maybe I'll sweep the dust bunnies under my rug. I don't know, you know? But I'll be hanging out in my apartment. And if you guys have questions during the test, or if you need a hint, you can shout, hey, Brendan, question, and then everyone can kind of listen into the conversation and hear what hint I give you. I think that could be useful because sometimes you're on the test and you're getting really screwed up, and I can just be around to solve problems. Sometimes you can get really stumped, but if I give you a little push, you'll be rolling again, and I don't mind giving you a hint here and there. That sounds like a good idea too, right? All right. Let me do one last thing and just tell you the format of the test and what chapters or what parts you're gonna have to study. Wait, do any of you actually own the book? How many of you own the book? I thought so, okay. So if you don't own the book, fine. But here's what you're gonna need to do. You're gonna need to read through your notes, okay? But most importantly, you need to re-solve the homework problems. That is pound for pound the greatest way to study for the test, is to redo the homework problems and see if you can do them on your own. I've already made you a perfect cheat sheet because I've done the problems with you, correct? So I would look at the questions and see if I could solve them without the answer key there, and then look at the one that we did and see how yours stacks up. That would actually be a pretty good way to learn. Let's face it, most of you probably won't study, and so the next time I see you will be the next time you think about this, which is during the office hour session. That's fine, that's what that's there for, but your grade will go up if you read the notes and resolve the homework problems. Just saying, it's up to you. All right, let me tell you what the format is. So the test is going to be 100 questions. It will all be multi-choice, A, B, C, D, E. That means you have a 1 in 5 chance or a 20% chance of guessing the correct answer. So even knowing no astronomy, you should be able to score 20 points just by filling in all the bubbles. Do you understand? All right. It will obviously be stressful. However, if you've been a good boy and girl or a good person and you've turned in all of your homework in your labs, it'll be fine. Whatever you get in the test, you'll still pass the class. Just do your best, okay? The test is stressful, but it's not going to cause you to fail. The only way you can fail the course is if you don't turn in labs and homeworks, okay? It's just that simple. Now, the first section is going to be a section on diagrams. And that's where I'll show you a picture or a diagram from our PowerPoint slides. And then there'll be a few questions asking you to identify the correct vocabulary term. So question 1 will be about this guy, and 2 will be about this guy, and 3 will be about this guy. And that's kind of a test of your knowledge of the diagrams and also your vocabulary terms, okay? For diagrams, I expect there to be around 30 points. And that means either 5 picks times 6 questions, or maybe 6 pictures times 5 questions. Probably 5 pictures, 6 questions each, okay? The next 30 points is going to be due to sort of general multiple choice questions. And for the general multiple choice questions, I'm going to ask you something that could be technical, but it might not be mathematical. Like I might ask you, what's Kepler's second law of planetary motion? Or I might ask you, what's the definition of temperature, or something like that, all right? The last section, which will be 40 points, is going to be your math applications. And for your math applications, the structure of it will be very similar to a homework problem, in that you'll be given a box with some givens. And the givens might be the synodic period of Mars, or maybe I'll give you the distance to Jupiter. And then I will break the math form into like 4 or 5 questions. And you'll have to go through in stages. So like usually in these problems, the first step is just to do a conversion. So I might ask you to just convert the period into seconds. And that will be basically, if you know dimensional analysis, you're able to get that. The other thing, then you'll have to apply a formula, maybe p squared equals a cubed, and you'll have to do something and get me the right answer. Oh, class, there is going to be a formula sheet on the test. Would you like, oh, I have a chat question coming in. Oh, that's okay. Do you guys want the formula sheet now so you can study with it? Does that seem like a good idea? All right. I think, yes, please. I think I can share a file. Excuse me here. Shoot. One sec. CCRI. Exams. You guys are 1010, AS1010 formula sheet. Okay. Do you guys all see that in your chat log? Does everyone have access to that? Can everyone see that? It says me to everyone. Let's take a look at that formula sheet together. Oh, I guess I can't click on it. Okay. It'll look something like this. You'll notice that it will have the conversion factors you need, right? So that's helpful. It also has constants of nature like big G, and it has the formulas. It will not always tell you what the units are. So like when you see p squared equals a cubed, you guys are supposed to know what p and a are, and you're supposed to know what units they are. Do you guys know what p and a are in this formula? If not, you need to study. What does p represent? What does a represent? And what units do they have? Whoa, talk to me, someone. No? Have I pushed you too hard? A is an AU. That's right, Adrian. Thank you. Adrian, I forgot you were even here. Okay. Show none. Oh. Hey, Adrian and Destiny. I forgot. I just showed my non-video participants. Oh. Oh, no, of course, Adrian's here. Sorry, I forget that I have you different in my logbook, so I get confused. I should put that in, actually. I should put your real name in here. Okay. I'm sorry, I lost y'all for a sec. Okay. Yes, Adrian. Sorry, Adrian, once you went dark, I immediately, okay, I've got you now, though. A is an AU. I think I'm choking on a candy bar here. All right. But what does it represent, Adrian? Look, p squared equals a cubed is definitely on the test. I'm sure you guys are running out of gas. I kind of am too, but yes, Megan, distance between the planet and the sun. What about P? What does P represent? Period of time, measured in what units, Megan? No, that's in Newton's version. Kepler's version is, yes, in years. Okay. That's okay, but clearly we all have a little bit of studying to do. You see what I mean? I kind of want you coming to the test knowing that stuff. I mean, if you look at p squared equals a cubed and you have no fucking clue what it means, well then, okay, fine, that happens, but that means you got to study a little bit, okay? I want you to know what P and A are. All right, I've berated you enough. Does anyone have any questions for me? Comments or concerns? Andrew.
I was just wondering if you could send me the link for the recording for the quiz from the summer session 1, because I missed the first question. I was a little late this morning.
Yeah, I think a couple of people were. Let's find that one, shall we? Today we did homework for lecture 6. This actually says lab 6 on it, but actually we didn't do lab 6 that day. So that's what's confusing, is I decided last minute to not do the lab. So this is basically, I have to send you the summer 1 version, right?
Yeah.
Do you see that in the chat log? Olivia, you missed the first couple of questions too, so you're gonna need that, right? I don't know who else was here, but Yimmersi, you might have missed a question or two, so you're gonna have to do that. So listen, I hope everyone's keeping up with their assignments. Everyone that showed up today, I think, has been doing pretty good. You guys are like the core crew. Yeah, the people who aren't turning stuff. Oh, Yimmersi, except for Yimmersi. Yimmersi, what's up? In both my classes, you owe me a lot of stuff. But you've actually been here for some of it, so I don't get it. All you need to do is upload it. What's going on?
I sent you an email letting you know that I needed technical support to come in because I was uploading all my work, but it was showing that it was offline. So all of my work was saying offline, and it said pending after I submitted it. So I had to get technical support, and it's doing the same thing all over again.
Okay, I should know the reason for this. I think I figured this out once. In the meantime, Yimmersi, you should probably email them to me because I keep a record here. I think I know, I can probably figure out what's going on here. When you go into like homework, right? You click on this, correct? Like homework 1. And then you're going down here to browse my computer and you're uploading the files there, correct?
Yes, I am. I have actually a picture of it. That way you can be able to see exactly what I saw. And then it was pending. It's weird. And it's doing it again.
Blackboard's buggy. Oh yeah?
I don't know.
Hold on, wait. Let me go to speaker view. Yeah, but that says current grade. What about going to the homework submission area?
Okay, so on the thing, oh yeah, it said.
Yimmersi, do you have this thing here where you click on homework and you go to submit, browse my computer, attach files? That's what you should be doing, right?
I did it on my phone and I did it on the computer, and both of them were saying that it's offline, unable to submit. And then once I got it to submit, it would say pending, like if it was a movie.
Right. Maybe your internet connection is spotty and so it's getting confused. I got an idea. Could you do me a favor? Because Yimmersi, in addition to keeping the Blackboard one, you can see that I also keep a grade book in Excel. So I think you should send me the pictures by email to bbritton@ccri.edu. In general, that's not as good, but that'll do in a pinch so I can get your grades in. Is that cool? I need you to label each email. Each email should say, and remember, Yimmersi, you're in both classes, so this can be wicked freaking confusing. You got to say AS1010, homework 1, and then you send me that.
Okay.
AS1010, lab 1. AS1020, homework 2. Label each subject of your email so I know what the homeworks are, okay? And send me one homework per email so I can monitor it all.
Okay.
That'll do until you can get your problems worked out, okay?
Okay.
Okay, cool. Any other questions? All right. Thank you for being with me, and I will see you guys 10 o'clock for test prep. We'll do maybe 10:15 to noon. We'll do test prep, okay? All right, you got it.